Now, Henry will be our next speaker. I don't know if it is ready. Henry?
Hi, everyone. I'm ready here.
Yeah, I will introduce him. Yeah. Well, Henry will talk about. Sorry. Second. Yeah. Henry will talk about the enhancing security at the physical layer of wireless system application in code domain NOMA. I will introduce to Henry. Yeah, Dr. Henry Ramiro Carvajal received his bachelor degree in electronics and telecommunication engineering from the Universidad de las Armadas, ESPE, Ecuador, in 2009, graduating in the top student among all technical and engineering programs. He later earned his master and PhD degrees in electrical engineering from the School of Electrical and Computer Engineering at the University of Campinas, Brazil in 2014 and 2018, respectively. In 2018, he served as director of the Technology Transfer Division at the Secretariat of Higher Education, Science, Technology, and Innovation, CENESID, in Ecuador. He obtained the HCIA 5G certification from Huawei in 2020 and has been a senior member of the IEEE. Since 2022, since 2024, he has served as Vice Chair of the IEEE Communication Society, Ecuador section. Dr. Carvajal is currently a faculty researcher at the Universidad de las Américas, UTLA, Ecuador. He is the author of more than 50 high-impact journal publications and actively participates as reviewer and technical program committee member for various international conferences and journals. His research interests include digital communication, wireless system, orthogonal and non-orthogonal multiple access, multiple user detection, MIMO, reconfigurable intelligent surfaces, fluid antenna system, physical layer security, machine learning, and emerging technologies for 5G and beyond 5G networks. Continue, Dr. Carvajal, please.
Okay, thank you, Paola. So just one question. Can you see my screen?
Sí, yes.
Okay. Okay, good afternoon here in Ecuador. Good evening in Europe. I would extend my gratitude to the organizers of this insert training event, in this occasion hosted by Universidad de las Américas. So I commend this initiative for creating an international event. It is a space for collaborative environment focused on addressing the critical challenge of security and privacy in next wireless communication systems. So for me, it's an honor to be part of this effort here. Okay, I'm going to talk to you about a technique called non-orthogonal multiple access, which is related with Internet of Things. This is a very interesting topic. In the previous presentation, Chamita and Bart talked about the challenges that implies ensure security for Internet of Things devices. So my presentation is related in this line or in this topic. So for beginning, let me talk about a little bit about 6G communications. So we know that mobile networks have mostly focused on commercial aspects in their development over the years. So, however, the push for 6G wireless communications that is sometimes called as 6G humanity aims to prioritize a more human-centered approach. So the goal of 6G is not just technological advancement, but also contributing to sustainable goals. In addition, addressing societal challenges and supporting economic growth. So the emphasis is on making technology more inclusive and human-oriented, benefiting various industries and seeking for positive changes. For this purpose, we require technological advancements, and in this context, we can observe here that centimeter positioning, artificial intelligence, terahertz technologies, and cyber physical security are interesting technologies for ensuring security in future 6G communications. Okay, in this figure, we can see that physical layer security, we observe here like phy security. This is a novel technology for 6G physical layer. In particular, this figure obtained from the 6G flagship indicates that this technology has not so high uncertainty, but a considerable impact on wireless networks, okay? So in a general way, a wireless network may have some limitations, for instance, open wireless access medium, limited bandwidth, system complexity, limited power, limited processing capacity. So for this reason, conventional approaches to ensure security in wireless network may prove insufficient in certain emerging scenarios. So mainly due to the low computational capabilities of some devices. So in particular, I'm talking about Internet of Things devices, okay? Well, so what is the idea behind physical layer security techniques? Here in the slide, you can see we have a transmitter named as Alice, a legitimate receiver named as Bob, an untrusted receiver or an eavesdropper, which is named as if. So physical layer security techniques aim to guarantee reliability for the legitimate link. This is the link between Alice and Bob, and secrecy for the wiretap channel. So in other words, the link between Alice and Eve. Okay, so when reliability, we mean that Bob can decode the message transmitted by Alice without error. This is theoretical. This is perfect reliability. And by secrecy, we mean that if does not obtain information from the message transmitted from Alice to Bob. In this case, we have perfect secrecy. In practice, in real system, this doesn't occur at all. But this is the main idea. So we have different metrics in this area. For instance, secrecy outage probability, which is the probability that the channel capacity of the legitimate link minus the capacity of the wiretap channel falls below a threshold. Or even we also have the error probability, where the aim is for this probability to be extremely high for the eavesdropper. Okay, well, this is the aim of physical layer security. So now I'm going to give a brief introduction about non-orthogonal multiple access. This is a very interesting technique that want to guarantee a lot of devices connecting to the same base station. This is one of the aims of 5G or 6G when we want to ensure massive connectivity. Okay, so here we have first orthogonal multiple access. Specifically, orthogonal multiple access is used in 4G, in the first releases of 5G. And the idea here is that there is no interference among users within the same cell. The idea here is that one user or one symbol is transmitted in one subcarrier, okay? So in the other side, we have non-orthogonal multiple access. Specifically, there is interference among users within the same cell, and the interference can be mitigated using multi-user detectors at the receivers. Obviously, they are more complex than the receivers that are used in orthogonal multiple access. Okay, so the idea of this non-orthogonal multiple access is to ensure communications for 1,000 devices per cubic meter. Okay, that is one of the KPIs in 6G communication. And for this reason, non-orthogonal multiple access is an interesting option for future wireless systems and for IoT networks. Okay, so the idea here, you can see that I have the information for one or two users transmitted over the same subcarrier. So we have interference. We have two different proposals for non-orthogonal multiple access. The first of them is power domain non-orthogonal multiple access, and the second one is co-domain multiple access. The idea is to divide or to separate the information of the same users transmitting in the same subcarrier using the power domain or the code domain. Okay. Well, among the various codomain non-orthogonal multiple access techniques proposed in the literature, here we have a sparse code multiple access. This is a very interesting technique. This technique was proposed in this paper here in this conference in 2013. Basically, the concept is that different bit strings are directly assigned code words that belong to different books of multidimensional codes. It's a little bit difficult to understand this, but the idea is to create, using a Cartesian product, the idea is to create mother constellations that are multidimensional constellations that are obtained from the Cartesian product of QEN or rotated QEN constellations, okay? Well, what are the advantages of this technique? First of all, sparse code multiple access allows the system to be overloaded. What it means? It means that the number of users that are served by the system can be greater than the number of subcarriers in the system. Okay, this means that the system is overloaded. In addition, we have that we can employ a multi-user detector called based on belief propagation in the receiver, which is also based on the message passing algorithm in the receiver. This is a nearly optimal low complexity detector and that can be implemented, and we can obtain very good results with the implementation of this receiver. So here we have an example of a system with 4 subcarriers. Specifically, here we have 1, 2, 3, 4 subcarriers that can accommodate 6 users. 1, 2, 3, 4, 5, 6 users, okay? This means an overloaded system. Additionally, note that not all users transmit on all subcarriers. For instance, user 1 transmits in the first and second subcarrier, user 3 transmits in the first and third subcarriers, and so on, okay? And what is the idea? In this context, complex values created from these mother constellations are obtained. And the idea here is that these complex values and these complex numbers are transmitted in different subcarriers, okay? For this reason, this is a codomain technique because we're creating a kind of code for transmitting the different of the different users, and the idea is to recover the bits that this user transmitted on the receiver, okay? Well, and for instance, user 3 transmit this symbol here and this symbol here if he transmits, for instance, the bit 0, 1, 0, 0, okay? And then the idea is that all signals are summed, okay, and this information is received, and from this information received in 4 subcarriers, we want to decode information of all the 6 users, okay? And it is possible. If you want to learn some additional aspects about sparse code multiple access, in this moment the time is short, but if you want to download some simulations in MATLAB or some papers related with this, you can scan this QR code where I have shared for you some documents and some simulations related with non-orthogonal multiple access, okay? Well, so at the end of the previous year, we proposed a strategy for enhanced physical layer security, which was accepted in the IEEE Transactions on Vehicular Technology paper, a journal, and I'm going to discuss you now some details about this proposal. Okay, so let us consider the upling of an sparse code multiple access system where we have J users. Okay, here we have 1 user, 2, 3 J users. Okay, a legitimate base station. Okay, which is named as Bob, and a spying or eavesdropper base station that is attempting to decode information from these J users. Okay, so in the analyzed system, we consider a fading channel of the kappa mu type, which is a statistical model that aligns well with the random attenuation of the wireless channel in millimeter wave propagation environments. Okay, this is the system model that we have considered. And basically, as I mentioned earlier, the generation of codebooks or multidimensional constellations is derived from the rotations of multidimensional MQAM constellations. This process is carried out using orthonormal matrices. Here we have, for instance, a matrix for 4 dimensions, okay? And this matrix depends on the rotations parameters that we have here, lambda 2 and lambda 4, okay? So the proper selection of these parameters determines if the system is going to perform well or not, okay? It's important to indicate that not all rotation angles necessarily ensure optimal performance, and this was the center of our work, okay? So in the paper that proposed this technique called signal space diversity in 1998, the authors proposed the optimal rotation angles for Rayleigh fading. Okay. However, these analyses had not been conducted for generalized fading channels. For instance, the kappa mu fading channel that we have considered in our work. So in our work, we derived a metric, this metric here, that enables the determination of the base rotation matrices, or equivalently the base rotation parameters, to ensure the optimal performance of the sparse code multiple access systems. Okay, so the idea is to obtain the best rotation parameters, specifically lambda 2, lambda 4. What are the best rotation parameters? And this metric, this is one of the main contribution of this work, that we determined that this metric depends on the fading channel parameters and the rotation parameters. It is not unique, okay? And in this figure here, we have highlighted in red the regions where we obtained the best rotation parameters. Specifically, we obtained the value of this matrix L as a function of lambda 2 and lambda 4. And we have determined that in these regions, okay, we obtain the best rotation parameters in order to create these mother constellations that ensure the best performance for the sparse code multiple access system, okay? Well, so what is the idea here? Each user may have different rotations parameters because their channel experience independent fading. And here we have an idea to create an algorithm to ensure security. Okay, now with these tools at hand, we can generate small databases with the best rotation parameters for each user. So if user terminals have sufficient computational capability, okay, this information can be computed at the user terminals, okay, and at the base station, because the user terminals and the base station knows the information about the channel, okay? So it's important to note that the parameters for the channel between the users and the eavesdropper are different, okay? Here we have that the channel affecting this link, for instance, is different or is independent for the fading channel affecting this link. Okay, so therefore, even if the eavesdropper was aware of our metric, it could not determine the same rotation parameters as those for the link between the users and the legitimate base station, because remember that the rotation parameters are dependent on the fading channel affecting the link. Okay, so however, it's important to take into account that errors in channel estimation can lead to different rotation parameters, but we have also proposed the strategies to minimize this error. Okay, however, we can consider the worst case scenario in which user terminals lack sufficient computational capability or capacity, like in the case or in Internet of Things devices, okay? In this case, the base station determines the best rotation parameters and transmits them to the users, okay? So let us assume that the eavesdropper intercepts this information, okay? The eavesdropper obtained this database with the best rotation parameters. So the question now is, how do we protect the information transmitted by the users, okay? And the idea was the next. So we can proceed with the use of a unique secret key that is known only to the base station and its user. And this key is generated based on the estimation of the wireless channel. okay? Specifically on the fading channel, okay? So this fading channel has unique characteristics for the link between each user and the base station. In particular, we use the channel phase as because it exhibits significantly differently statistical behaviors for each user. Okay, so for this reason we use the phase of the channel. So as an example, we here this figure here. Okay, this figure here displays the probability density function of the phases for 4 different users. Okay, based on the parameters of the fading channel. Here we have changed the cap and mi parameters of the fading channel, and here we can observe that they are quite distinct, further complicating the eavesdropper task. Okay, because remember the secret key is created based on the random phase created by the fading channel. Okay, then these random phases are used as initial parameters to create chaotic sequences, and from these sequences we can establish the rotation parameters that both each user and the base station should use for encoding and decoding process. So basically we can generate chaotic sequences with various numbers between 0 and 1. And from this, we can create a bit of sequences that results in a decimal number, indicating which rotation parameter to select from the database. Okay, this prevents eavesdropper from determining the rotation parameters used in the transmitting event. Okay. Well, to conclude, let me present you some numerical results. So initially, we're going to analyze what happens solely with the bit error probability, okay, of the legitimate users, okay, when using the rotation parameters obtained with our metric, okay. So these figures here illustrate the average error probability as a function of the signal to noise radio, the normalized signal to noise radio. And if we compare in the figure of the left, we have employed the optimal rotation parameters that we have obtained with our proposal. And in the right side, we have used non-optimal rotation parameters. Specifically, here we have used the rotation parameters that Viterbo Boutrous found for Rayleigh fading. Okay, and if we compare both figures, we can observe that we obtain a lower average error probability for this SMA system when our rotation parameters are used. Okay, this is the first result and the first contribution. So it means that our metric is working well. Okay, and here finally we have the average error probability for both the eavesdropper and the sparse code multiple access system frame. Okay, meaning in other words, this frame is the average of the average error probability for all legitimate users. Okay, so once again, here we have the average error probability as a function of the normalized signal to noise radio. And we have considered different levels of error in the channel estimation. Here, for instance, in the left image, there is no error in channel estimation, while in the right side, we have a higher level of error of estimation in the fading channel. So the issue with the channel estimation error is that the legitimate base station and the user's terminals may estimate different phases or parameters of the fading channel, which can lead to the use of a different rotation parameter in the encoding and decoding processes in the sparse code multiple access system, which is not good. Okay, so however, we have proposed some strategies to combat this, and the results indicate that the eavesdropper here, this is the average bit error probability of the eavesdropper. The eavesdropper has an extremely high bit error probability, implying that this device cannot decode information of any user. Okay. Furthermore, the proposed strategy is quite robust against channel estimation, and noted that there is no significant difference in performance between the results in this figure here and this figure here, and we are obtaining a good performance for the legitimate users, and the eavesdropper cannot decode the information. Okay. Well, in summary, non-orthogonal multiple access emerges as a promising solution for Internet of Things networks, and it aligns well with the objectives and the key performance indicators of 5G and 6G by enhancing connectivity, increasing throughput, offering flexible resource allocation, and optimizing spectral utilization. Okay, so the idea here in our proposal was to create different codebooks that are unknown to the eavesdropper, and the generation of these codebooks ensure a good system performance for the users, for the trusted users, but uh, the idea is that the eavesdropper can know the code, all the information. Okay, that's all. Thank you so much for your attention.
Thank you so much, Dr. Carvajal. If someone is having some question, please. Yeah, we have one question. What are the computational complexity analysis to execute this security mechanism, especially considering capacity-limited devices?
Yes, this is the main idea behind this proposal, because remember that Internet of Things devices don't have a high computational complexity. So the idea here, as I said, if the final devices has a high computational complexity, they can calculate this using this simple metric that we obtained. However, if they don't have enough computational complexity, we can do that the base station can calculate this metric and obtain the base rotation parameters, which is not complicated, okay? But in the case that the final devices cannot calculate these metrics, the base station can calculate them easily, and then the base station can transmit this information to the final devices, to the user terminals, and then using our proposal, both the base station and the terminal users can establish which one of the parameters must be used in order to ensure the best performance, and this information is changed, see, after several transmissions in order to make the life of the eavesdropper more difficult.
Paola, you unmute, I think.
Yeah.
Sorry, thank you, Bart. I have one question. How about to vulnerability? No, what types of physical layer attacks are most relevant in the context of CD NOMA that you have talked?
Okay. In the case of non-orthogonal multiple access, we have different problems. One of the problems is that the radio resource is shared by different users. Okay, for instance, let us consider power domain NOMA, non-orthogonal multiple access. Here we have the information of 2 or 3 users is transmitted in the same radio resource. And the problem is that if we have one untrusted user in this group of users, this user can hear the information that is transmitted to the other users. Okay, and for this reason, we need some additional strategies to complement traditional cybersecurity algorithms that are more simpler, that can be used for simple devices like these devices of Internet of Things. So this is one example of this kind of attacks.
Okay, and I don't know. Another question that is going by my in which real-world application or network scenarios is secure CD NOMA or is more beneficial?
Okay, for now, it's just a proposal. The idea is to ensure that future 6G networks can support 1,000 devices per square per cubic meter specifically, and a scenario where we can this number of devices maybe is related with industrial scenarios. Okay, maybe in our home, in our house, we don't have this number of devices, but I think that these proposals related with non-orthogonal multiple access and this idea of massive communications is very useful in industrial environments.
Okay, thank you so much. Henry, I don't know if someone is having another question. Yeah.
I think there is a question in the chat.
In the chat. Oh, okay. Let me see. Okay, see, it's another one. Please, could you mention some project to apply for our country or city with this technology?
Okay, intelligent cities. I think this is a good alternative where we have that some devices that use low bit rates and they do not require a very low latency. Maybe are an option
exactly
for this.
Yeah. Thank you so much. I don't know, Bart, if you want to add something.
No, I think this was a very interesting presentation. It seems that some of these results you were showing in the diagrams are coming from perhaps your recent publications. So, I mean, everyone has access to Scholar, but I think it would be nice to leave some contact details or share some contact details, Paola, especially with the rest of the consortium. So here I'm referring to Ensure 6G Consortium because, of course, we will be doing some cross collaboration. Yes.
Okay,
with
I
Henry,
forget to show this slide. Here you have my personal website and you have my email. So if you need or you have some another additional question or if we can work together in some project related with this technology, please write me.
Yes. Yeah, so thanks for this, and I will be definitely checking out the profile because some of this research stuff is new to me, relatively new. So that'd be great. And I guess we now have a lot of people and keeping up this academic spirit. Perhaps some of the new joiners don't know, but as Paola mentioned at the beginning, this is a collaborative project between now 14 different countries. There are a total of 343 exchanges planned over the next 4 years. So it's extremely likely that people you see here today online, they will be actually visiting your facilities at some stage over the next few years, and vice versa. I'm sure there will be people from UDLA coming over to Europe, and you're very welcome to visit all of our partners. So yeah, I mean, I think exchanging this contact details and research articles, I think it's extremely valuable. For this, I think we will also do a follow-up, maybe like a blog post where we can link also some of your emails and have be able to extend your network beyond what you currently have. But yeah, I don't have technical questions. I will definitely deep dive into your work, which seems to be very relevant and very interesting. And especially that one last comment. There are not a lot of because the last questions were about the physical layer specifically. There is a lot that needs to be done in the physical layer, and not a lot of companies or universities that do work in the physical layer. There was a clear shift towards, AI explainability of AI, but there is still, we're lacking for partners, for example, that work specifically in the physical layer, and then also executing tests and doing validations of these research ideas is also not straightforward because it's not a simple Python scripting that you can do. It's using things like, for example, OpenRes. We work with reflective intelligence surfaces, and this is actually a very physical test bed that needs to be distributed. The 5G test beds themselves are quite distributed when it comes to the physical distribution. And lastly, I just want to say that if you want to be publishable lately, you should execute tests in real physical environments. Because there is a lot of work. It's quite saturated in the research world. People working with different data sets and doing theoretical slash semi real life testing. Now we need things like 5G and future beyond 5G testbeds. Just as a bit of advertising in UCD, UCD Nets Lab, we have a 5G ORAN testbed that is not extremely open, but it is very open. So all the data sets that we generate with real-time data, the actual telecommunication like data is open to the outside world and to the every researcher possible, unlike with the actual telecommunication companies. So we work with some great teleco companies, but when we ask them for data, they just turn around and walk their own way because they don't want to share anything, and that is understandable. They deal with real users. We deal with emulated users or the devices that generate traffic that is not sensitive, but it still generates data. So that's my observation from the last, I think, couple of months of trying to figure out what is going on in this 5G publishing space. So that is, I think, something you can look into. I can also link in the blog post the 5G ORAN testbed that I was mentioning just now, and you are welcome to use it. Okay, thanks, Paola. That's my last comment, and we can go back. I'm not too sure what left in the agenda.